On Friday, we went way back and learned to add again. We learned that in grade 1, we were taught to add 3 plus 4. When we did that in grade 1, it equaled 7 every single time. We also reminded ourselves that in grade 6, we learned to add negative 3 plus 4, or 3 to the south plus 4 to the north, which gave me 1. So 3 plus 4 was sometimes equal to 1. Maybe we had 3 to the north and 4 to the south. In that case, it would be equal to 1 again, but 1 to the south this time. On Friday, we learned to add 3 plus 4 if they weren't in the same plane. So if we had 3 to the east and 3 to the north. Remember that when we had two vectors that we were adding together in two different dimensions like that, east and north, or south and west, or something like that, remember that we had to get a right-angled triangle vector diagram. But to draw a vector diagram, we first had to learn to draw vectors. A vector, if you remember, is a line segment with an arrow on the end of it showing the direction. A vector diagram is a series of vectors that are drawn, what's the term we use? Front to back. So this is the front of one vector. This is the back of the same vector. If we have two vectors like this, then we have to make sure we either draw that vector diagram like this, front to back, or like this, front to back. Either one, it doesn't really matter. Both of them give me the same thing. Just like in grade 1, 3 plus 4 was equal to 7, and 4 plus 3 was equal to 7. Didn't matter what order we added them in grade 1. It doesn't matter what order we add them in grade 11 either, even when we're adding vectors together. But we do have to draw them such that they're drawn front to back like that. Now, the sum of those vectors, which is really what we're looking for here, right? To add those vectors together, the sum of them is what we call the resultant vector. Sometimes we give it a symbol R. That resultant vector kind of doesn't follow the same rules as the rest of the vectors, our blue vectors here. The resultant vector is going to be drawn from start to finish. So from the back of the first vector to the front of the last vector. That's our resultant vector in the first vector diagram. This would be our resultant vector in the second vector diagram. What do you notice about those two resultant vectors? They look the same, right? And they should, because if we're adding this one x plus y, or switch it around, y plus x, we should end up getting the exact same resultant vector in both cases. Make sense? All right. Well, how do we find the value of that resultant vector? How do we add 3 plus 4 if it's in two dimensions like this? Once we draw our vectors, and then once we draw our vector diagram, and once we have a right-angled triangle vector diagram, we do what? We do a little trigonometry in the Pythagorean Theorem. So we would say that, well, normally we would say a squared plus b squared is equal to c squared. What are we calling c here now, though? R. So it's going to be a squared plus b squared equals r squared, right? And then you're going to solve for r by saying the square root of a squared plus b squared. Now, there is one more thing that we have to include here. What is it? Besides the magnitude of my resultant vector, I also need what, Holly? I need the direction. Now, the direction isn't quite as simple as it was when we were adding vectors in grade 6. Hey, negative 3 plus 4 was equal to plus 1. 3 plus negative 4 equaled negative 1. That was simple to include direction, right? It was either north or south. The direction's harder here. What do we got to do to find the direction in this case, Kessler? Sorry? Yeah, find the angle, right? And that angle is always going to be drawn from the start. So we draw it right here, or we draw it right here. How do we know that's the start? Well, look back to where you started drawing your vector diagram. At the very beginning, that's where I draw my angle, at the very beginning. Now, I'm going to use a trig function to calculate that value of theta. And normally, the trig function I'm going to use is the tan function, because I would normally have the value of the opposite side of the triangle and the adjacent side of the triangle. So r is equal to the square root of a squared plus b squared, and theta would be equal to the second function tan, or inverse tan, of opposite over adjacent. All right, we had 3 questions that I left you with for homework. Okay, just on your worksheet, questions 1, 2, and 3. I'd like to take a look at those questions here now, going over, or at least illustrating what we've just gone over here in the last couple of minutes. So let's take those questions out here now, please. First one looks like this. Question 1, we have 20 meters to the east, and then we have 10 meters to the north. Okay, those are already drawn for us, at least the bulk of the vector diagram is drawn for us. Notice that these are drawn, or this one is drawn front to back. The front of the 20 is drawn to the back of the 10. So far this is drawn correctly. What else do I have to draw on this before I go and do any calculations here? Yep. I got to draw R, and R is going to be drawn from start to finish, so it's going to look like this. I like to do it in a different color or a dotted line. It doesn't really matter. You can draw it as a solid line the same color. I like to distinguish it in some way, though. Either make it a dotted line or use a different color. Let's find the value of R here now. R is equal to the square root of 20 squared plus 10 squared. 20 squared is 400, 10 squared is 100, square root of 500, I think ends up equaling to 2 digits, 22. Is that right? 22.3, I think it is. The 2 digits, I think it's 22 meters. Now, the value of theta, I want you to tell me where I'm going to calculate the value of theta. Position 1, position 2, or position 3? 1, 2, or 3? Where is it? Who says 1? Okay, 2, 3? It is position 1 because that's the start of my vector diagram. So let's say theta now is equal to the inverse tan, second function tan, of opposite over adjacent. Why is the 10 the opposite side of the triangle here? Yeah, it's not touching the angle. There's one side of this triangle that doesn't touch the angle. It's the opposite side. The adjacent side is the other side that's not the longest side. Right? The hypotenuse is the longest side, always. The opposite is the one that's not touching. The adjacent and the hypotenuse both touch, but the adjacent isn't the hypotenuse. It's not the longest side. So let's do this. Let's do this on the calculator up here just to make sure that you guys can all do this. Let's say theta is equal to the inverse tan. Make sure you're in degree mode. What was the trick for that one? The check? Now you go mode, or nice little quick check is sine 90. If it equals 1, then you're in degree mode. So you're in the right mode if sine 90 equals 1. And if you're not in the right mode, then you're going to have to go into mode and switch it around down here. Okay, the inverse tan will go second function tan. That's your yellow button or your blue button, depending upon which version of the calculator you have. Second function tan of 10 divided by 20. Let's finish off the brackets. And we get 26.56 or 27 degrees. Okay? Now, a little bit later on, we're going to learn to express that 27 degrees relative to something. Because it should really be relative to something, right? If I say my position is 3 meters away from something, well, what do I mean by that? Am I 3 meters to the north or 3 meters to the south, right? I have to have a reference point. And I don't have a reference point here yet, but we're not going to worry about that right now. We're going to just focus on just calculating the angle right now, and then we'll worry about the reference point. All right. Let's do question number 2 here. 2 says we got 15 meters this way, and then we have 10 meters this way. Is that drawn okay? Yeah, front to back. My resultant vector is drawn from start to finish. Where do I put the arrow on it? This end, end 1, or end 2? End 2, because it goes from start to finish. Where you began drawing it to where you ended it. This is going to be called R, and we're going to find the value of R by the Pythagorean Theorem. It's the square root of 15 squared plus 10 squared. 15 squared is 225, 10 squared is 100, so it's square root of 325. On the calculators, let's go square root, second function squared, 325 gives me 18. Where am I going to draw my angle? Okay, watch carefully here. Position 1, 2, or 3. 1, 2, or 3. Where's it going to be, Nick? Good, position 3. 1, 2, 3. It's going to be drawn at position 3 because that's the start of my diagram. That's where I began to draw the vector diagram. So we're going to say it's the inverse tan function of opposite over adjacent. What's the opposite side here, the 15 or the 10? We know that's not R, right? We know it's not the red one because that's the longest side. What's the one that's not touching the angle? It's the 10. So we're going to say it's the inverse tan of 10 over, well, the other one that's not the longest is 15. The inverse tan of 10 over 15. So let's on our calculators go second function tan, 10 divided by 15, and the bracket. 33.69 degrees or 34 degrees. And once again, there needs to be a reference point there. 34 degrees from what? We'll worry about that later on. Okay. And finally, one more here. For now, at least, one more. It's our third one where we have 10 meters this way, and we have 5 meters this way. The resultant vector is drawn from start to finish. Which end does the arrow go on here? End 1 or end 2 here? Danny, which end is it going to go on? It's going to go on end 1 there, from start to finish. Where's my angle go? Position 1, 2, or 3. 1, 2, 3. Which one is it? Position 2. Always drawn at the start there. Let's find the value of R. It's the square root of 5 squared plus 10 squared. Let's show this one on the calculator, actually. My suggestion for this is to go 5 squared plus 10 squared equals, and then let's square root that with the second function answer. Gives me 11.2 or 11 meters. Theta is drawn at the beginning. It's going to be the inverse tan, second function tan of opposite over adjacent. What's the opposite side? 5 to the 10. It's not the red one, right? Because the red one's the longest. What's the opposite side here, Mallory? Good. 5. And the adjacent side, of course, is, well, it's not the red one because it's the longest, so it's got to be the 10. The inverse tan of 5 over 10. Second function, tan, 5 divided by 10, and the bracket, you get 27 degrees. Relative to something, but again, we're going to worry about that coming up a little bit later. You guys feel comfortable with that? Good. Good. Well, in grade 1, you learned to add 3 plus 4. In grade 6, you learned to add 4 plus negative 3. In grade 11, you learned to add 3 plus 4 when we were talking about 2 different dimensions, east and west. But what if you were given a question that said 4 plus 3 plus 9? What if you had 3 numbers? Well, in grade 1, you could still do that, right? Because you're adding scalars in grade 1. And in grade 6, when you're adding vectors in 1 dimension, you could still do that. 4 plus negative 3 plus positive 9, or whatever the case may be. Okay, you could quite easily do that. How would we do it now? How would we do it now? Well, if you want to add, let's say, 4 plus 3 to the south plus 9, let's say, to the east, we draw a vector diagram like this. But what's the problem with that vector diagram? What's the goal? You guys remember what the goal is? To always get a right angle triangle. Is that a right angle triangle? It's not even a triangle, let alone a right angle triangle. We can still draw a resultant vector from start to finish, but we got to do something with this to get a right angle triangle, because we don't have one right now. So what are we going to do? We got to use what we call vector components when adding more than two vectors at the same time. What do I mean by that? Well, for each of the vectors we have, the example that I just gave you, the three vectors, we have to take the x components and the y components of each of those vectors. Then we have to add them together. What do I mean by the x components and y components? Well, this is my x-axis. This is my y-axis. So what I have to do is figure out how much of each vector is on the x-axis and how much of each vector is on the y-axis. Then I'm going to combine all of the x, combine all of the y, and then get a right-angled triangle vector diagram and do exactly the same thing as I did for homework over the weekend and exactly the same thing as I did when I just checked those over. So what does that really mean? Let's put it into practice here with a question. My question says, my first one says, add these three vectors together. 25 to the north, 20 to the east, and then 30 to the north. The first thing we're going to do is draw this out, same as we did before, but when we do that, we're going to see that we don't have a right-angled triangle vector diagram. Still a vector diagram, but not a right-angled triangle vector diagram. 25 to the north. Okay, that's to the north. Then we got 20 meters to the east. This one's drawn a little bit shorter because it's not quite as long as the 25. And then we got 30 meters to the north. Drawn a little bit longer because it's 30 meters instead of 25. Is that okay? Remember to draw them, even if we're drawing three vectors or drawing 14 vectors, remember to draw them front to back. Jillian, are they all drawn front to back? What's not? What's not drawn front to back? Okay, the 25 meters is drawn, right? This is the front of the 25, the back of the 20. The front of the 20, the back of the 30. Is that okay? Yeah, I could draw them like that. Now, I could have switched the order of them around, right? It wouldn't have made any difference there. Diagram would have looked different, but my answer would be the same. Where am I going to draw my resultant? Well, from start to finish. Which end does the arrow go on? N1 or N2? It's going to go on N2. And what's the value of that? I don't know. Can't do some trigonometry or anything on that because I don't have a right angle triangle. Now listen carefully because this is what sets this one apart from the last three questions we just did. I want you to break it up into x components and y components. And remember, everything on this axis is x, everything on this axis is y. Let's take a look at each of these vectors here and see how much is x and see how much is y. Look at the 25, the first one. How much of that 25 to the north is x going this way? How much of that 25 goes this way? 0. 0. How much of that 25 goes this way? 25, all of it. Does that make sense what I just did? I took my first vector and got how much of it was horizontal x and how much of it was vertical y. Next one, 20 meters. How much of that one is horizontal? How much of that one is x component? Zach, what do you got there for that 20 meters? How much of that is on this axis? 20, all of it. And how much of that 20 meters is on this axis, the y-axis? 0, none of it. And finally, the 30 meters, how much of that 30, Logan, is on the x-axis? This one, this axis right here. None. Good. And how much of that 30 is on the y-axis, Nicole? Sorry? 30, all of it. All right, so now what I want you to do is add them up. 0 plus 20 plus 0 is 20. 25 plus 0 plus 30 is 55. Now, watch carefully. Remember what I said when we started this whole deal on Friday? The goal is to get a right-angled triangle vector diagram. I had a vector diagram, but it wasn't a right-angled triangle vector diagram. This is the step that's going to get me to that right-angled triangle. I'm going to say 20 on the x-axis. And then I'm going to say 55 on the y-axis. Could I have drawn it the other way around, 55 then 20? Sure, I could have. As long as I do it front to back. Front of the 20 to the back of the 55, or it could have been front of the 55 to the back of the 20. That wouldn't really matter. Now I'm going to draw my resultant vector from start to finish. So the resultant vector going to be drawn, the arrow on the resultant going to be drawn at end 1 or end 2. End 1 or end 2. All right? It's going to be on end 1 because that's the end of it, right? That's where it's going to. What do you notice about those two red lines that I have drawn, though? Those two resultant vectors that I have drawn. They look pretty much the same, right? It's not a coincidence. I've just taken this diagram that looks a little bit more complicated because it's not a triangle, and I've turned it in to a relatively simple right-angled vector diagram triangle, and one that we know what to do with because we've done several of those questions here already. What's the difference between this question and the questions you had for homework? You had to turn it into, you have to turn this question into the question you had for homework. You had a right-angled triangle in those questions. In this one, you got to get a right-angled triangle. Let's find the values here. R is equal to the square root of 20 squared plus 55 squared. Let's say on the calculators, 20 squared plus 55 squared. Let's not forget to square root that. Get 59 meters. And theta is going to be drawn at position 1, 2, or 3. 1, 2, 3. It's going to be position 2. Yeah, it's going to be right here at the start. Theta is going to be the inverse tan function of opposite over adjacent. Jonah, what's the opposite side of this triangle? It's not R, right? Is it the 20 or is it the 55? Good. It's the one that's not touching the angle. So we're going to say it's 55 over, well, the only other one we have is 20. So say second function 10 if you're in degree mode, 55 divided by 20. We get 70 degrees. Relative to something, but once again, we're going to worry about that later on. Here's a quick question, a little aside. Unless you switch from degree mode to radian mode yourself, unless you physically switch it from one mode to another, what's the only way that it's going to switch modes? Like, how's it going to do it without you consciously doing it? When does it switch to radian mode? When your calculator is reset. So listen carefully. Before your unit test, I won't do this before quizzes because it's just a time-consuming thing. But before a unit test, we'll reset your calculators. It will go back to radian mode automatically. What are you going to make sure you do? Switch it to degree mode. And I'll try to remind you to do that so that you don't go through a test in radian mode. All right, let's do another example here, and then we'll set you free on a couple of questions here. Can I erase that? This one says we want to add 10 meters to the east, 15 meters to the south, 12 meters to the east, 20 meters to the south. Hey, if I was to give this question on a test, odds are somebody would say, oh, I can do that. 10 plus 15 is 25, plus 12 is 37, plus 20 is 57. Have we added those vectors? No, we've added scalars, not vectors. We found the distance. That would be the distance traveled, right? Not the displacement. Let's draw this out. We have 10 meters to the east. We have 15 meters to the south, front to back, 12 meters to the west, going a little bit longer than the 10. And then we have 20 meters to the south. Is that diagram okay? We got it drawn front to back, front to back, front to back. That's good, yeah, that's good. My resultant is going to go from start to finish. And we're going to label it R here. That's a really ugly looking one. So what are we going to do? We're going to turn it into a right angled triangle. We're going to do that by going through our X components and our Y components. What's the X component of the 10? How much of that 10 is on this axis, the X axis there? 10. How much of it's on the Y axis? 0. Well, here's a good one. See what you can do with this one, huh? How much of that 15 is on the X axis? 0. How much of that 15 is on the Y-axis? Negative 15. Good. Danny, why do you say it's negative 15? Good, because it's going south. Negative 15 because it's going to the south. Excellent. How much of that 12 is on the X-axis? Negative 12. All of it, but it's negative because it's to the west. How much of that 12 is on the Y-axis? 0. And finally, the 20. Alex, how much of that 20 is on the X-axis? 0. And Taylor, how much of that 20 is on the Y-axis? Negative 20. Good. You guys are superstars with this. Let's add them up. 10 plus negative 12 gives me negative 2. 0 plus negative 15, 0, negative 20 gives me negative 35. Let's redraw it. Negative 2. Negative 2 is on the x-axis, right? I've got it clearly labeled here, x. So let's draw it 2 to the west. And then we're going to say negative 35. It's drawn much, much longer because it's about 17 and a half times longer than the 2 should be. My resultant vector is drawn from start to finish. What do you notice about the 2 red resultant vectors? They should be the same, right? But remember what I said, you want to draw it as much to scale as you can, but you're not using a ruler, so it's not going to be perfect. If you used a ruler and a protractor, it should be exactly the same. If it's not perfect, I can live with that. We know how to do this, right? Find the value of r. Square root of 2 squared plus 35 squared. I don't know what that's going to be, but I know it's going to be real close to 35. 35.05, which rounds to 35, right? So basically, if you go 2 meters to the west and then 35 meters to the south, you're pretty much still going to go, your displacement is still going to pretty much be 35 meters. Theta, drawn up here at the start, it's the inverse tan of opposite over adjacent. What's opposite, Nicole, to this one? 2 or the 35? Good. So the adjacent's 2. Don't calculate this yet. Make a prediction. What do you think you're going to get for the angle? Small or big? Small one or big one? Really big, right? What's it going to be close to? Close to 90. It's not going to be over 90, but it's going to be real close to 90. I'm going to guess like 89 degrees. Okay. The inverse tan here, and I honestly don't know what it's going to be. I'm just guessing the inverse that it's going to be about 89. Inverse tan of 35 divided by 2 gives me, oh, okay, I was off by a bit, 87 degrees. So not quite as big as I was predicting, but still really big. Now remember, it should be relative to something, but we're not losing any sleep over that yet. That's coming a little bit later on once you've mastered this stuff. Good? All right, what I'd like you to do right now is, sorry, not right now. What I'd like you to do after you take a quick little break and get up and jump around and go get a drink is to do questions 4 and 5 on that worksheet. All right, let's have a quick look at those two questions here. Question number 4 says 10 meters to the east, 5 meters to the north, and then we have 15 meters to the east again. My resultant vector is going to be drawn from start to finish, like this. There's no point in even drawing the angle in right now because I don't have a right angle triangle. I don't even have a triangle, let alone a right angle triangle. Well, let's get a right angle triangle. We're going to do that by breaking it into x components and y components. Remember, x is this and y is this. So everything on the x-axis, everything on the y-axis. How much of that 10 meters, Emma, how much of that 10 meters is on the x-axis? 10 meters, good. How much of that 10 meters, Shay, is on the y-axis? 0, good. Liam, how much of that 5 meters is on the x-axis? How much of that 5 is on this horizontal axis? 0, good. How much of that 5 meters, Kelly, is on the y-axis? Good. How much of that 15 meters, Zach, is on the x-axis? Good. And how much of that 15 meters, who haven't I called on? Taylor, how much of that 15 meters is on the y-axis? Good. Let's add these up. 10 plus 15 is 25, and 0 plus 5 plus 0 is 5 meters. So let's redraw it. When I redraw it, it's going to look like this. 25 meters to the east. How did I draw that? How did I know to draw the 25 meters to the right as opposed to 25 meters up or down? We're in? It's the x value, yeah, and it's positive. Good. It's the x value and it's positive. So 25 meters to the right. The 5 meters I can draw right here. Is there anywhere else I could have drawn the 5 meters? Absolutely there is. I could have drawn it right here. Would that have been correct? Sure it would have. Sure it would have. It doesn't matter where I draw it, what order I draw it in, as long as it's drawn front to back. Okay, let's draw my resultant vector here now. It's going to be there. Where am I going to label my angle? Position 1, 2, or 3? 1, 2, or 3, Zach? Where am I going to draw my angle? 1, 2, or 3? Good. So let's say R, my resultant, the sum of the vectors. You could also call it the displacement, because when we add the displacements together, we get displacement. So add the vectors, the sum of the vectors, the resultant, the displacement, whatever you want to call it. 25 squared plus 5 squared. What does that work out to be? Who's got it? Yeah, you got to square root it. 35? No, not going to be 35. Does it work out just to be 25? Okay, 25 point something, right? But we round it to 2 digits, so it would be 25 meters. And theta, we're going to do this one on the calculator because this is the tougher one to do on the calculator. The inverse tan of opposite over adjacent. What's the opposite side here? That's the opposite side here, Nick. 5. And what's the adjacent side? 25, obviously. Say the inverse tan function. Second function tan of 5 divided by 25 and the brackets gives me 11 degrees. Some relative to something, but we'll worry about that later on. All right. And the last one, question number 5, a little bit harder, but same type of thing here. We had 8 meters down. We had 12 meters this way. Notice it's drawn a little bit longer. We have 10 meters. And we have 4 meters. The resultant is going to be drawn from start to finish. Although in the end, if I don't draw my resultant vector there, it doesn't really matter, right? Because I'm not analyzing this. I have to get a right angle triangle to analyze. That's what's important. Okay, x components, y components. How much of the 8? How much of the 8 is x component, Julian? X component, right, this way? 0, good. And Julian, how much is y component? 8, almost. Almost 8. Cool? Good. -8, good. 8, -8 because it's downwards, right? Good. How much of that 12 is x component? Logan, how much of the 12 is x? Good. And how much of it's y? Good. How much of the 10 is x component? I think I've pretty much got everybody here today, haven't I? Julie, how much of the 10 is x component? 0. How much of the 10 is y component? Good. How much of the 4 is x component? Alex, how much of the 4 is x? Good. How much of the 4 is y? 0. Add these up. 0, 12, 0, -4 gives me 8. 8, -8, sorry. 10, 0, 0 gives me 2. If we redraw it, it's going to look like this. 8 to the right and 2 up. We do have our resultant vector. And lo and behold, it looks the same as my original one. This. Zach Zed. Where am I going to draw the angle? Position 1, 2, or 3? Good. At the very beginning of my diagram here. Good. So find the value of r. We're going to say square root of 8 squared plus 2 squared. Square root of 68 is going to give me 8 point something. 8 point. Who's got it? 8.3. And theta is the inverse tan of, what's opposite here? 2 or 8, Kelly? 2. And what does that work out to be? 14. Good. Okay, real quickly here, I want to give you a taste of how to express it relative to something, that frame of reference. Okay. The 2 and the 8, where did I end up going? Like which 2 directions did I end up going? I went east and north. So we're going to either express this 14 degrees as east of north or north of east. How do I know which one to express it as? Let's replace the word of with from. So if I say east of north, that really means east from north. Or if I say north of east, that really means north from east. Your angle will always be measured from north, south, east, or west. It will always be measured from one of your 4 primary axes, north, south, east, or west. Can you tell me which one this angle is measured from? Is it measured from north, east, south, or west. It's measured from the east, right? That angle is measured from the east axis. That 8 meters is east, and I'm measuring the angle from the east, right? So I'm going to express this as 14 degrees north from east, or 14 degrees north of east. Of equals from. We got to see where we're measuring it from. It's always going to be from the north, south, east, west. And just replace it with the word of.